Hello, welcome back. We have been looking at how Lenz's law shows us that if we have a changing magnetic field, that will induce a current, and that the induced current will move in such a direction as to give a magnetic field that will oppose the change in the magnetic field. Now we're going to look at how we can use Faraday's law to give us the magnitude of that induced EMF. And so what we want to do first is look at Faraday's law. So Faraday's law tells us that an EMF is induced in a conducting loop if the magnetic flux through the loop changes. So we saw that if we have a change in the magnetic flux, that's when we will get an EMF that is induced. Now, the magnitude of the EMF, since it's related directly to the change in the magnetic flux, we can then say that the magnitude of the EMF is equal to the absolute value of the change in the magnetic flux with time. The direction of the EMF will be the same way as to drive an induced current in the direction given by Lenz's law, which we saw was the direction that opposes the change in the magnetic flux. So let's this time we used Lenz's law. Now let's use Faraday's law to try to show this as well. So let's look again at our sliding wire circuit. And we see that in our sliding wire circuit, we see that the magnetic flux in our sliding wire circuit is going to be equal to, here we have our magnetic field into the screen. So it'll be the magnetic field into the screen times the area. So it'll be times the area times the magnetic field. And that area we see is going to be equal to X, this distance here, X, times L, the length of our wire, the length of the wire that's fixed to the table. And X is what's changing. That's what's changing as we slide this piece of the wire here at a velocity V to the right. So we see that the area is equal to X times L. And so the area times B is going to be equal to XLB. So if we slide a conducting wire along a U-shaped conducting rail, we can complete a circuit and drive an electric current. We can find the induced EMF and current by using Faraday's law and Ohm's law. So let's start with Faraday's law. Here's Faraday's law. That tells us that the EMF is equal, the induced EMF is equal to the change in the magnetic flux with time. So we see that our magnetic flux is equal to XLB. So we can then rewrite this as the change in time of XLB. Now, what is actually changing, the only thing in here that's actually changing, L is constant, B is constant in this case. The only thing that's changing is X. So we can then rewrite this as dx dt of LB, dx dt times LB. And we know that dx dt is just the change in the displacement over the change in time. And we know that that is just equal to the velocity V. And so in this case, we can then put this in for dx dt, and we see that the induced EMF is equal to VLB. Now we can also then take this as our induced EMF and put that into Ohm's law. Remember, Ohm's law, of course, is Ver. So I always write that first as Ver. And then I can rewrite this as I equals delta V over R, where in this case, that is equal to our EMF, our delta V is our EMF in this case, our induced EMF over R. And so we can rewrite this as I equals our EMF over R equals VLB over R. And this is exactly what we found before. So we figured out that our induced current, just by using Faraday's law, we also figured out that our induced current is equal to VLB over R. So let's now look using Faraday's law and try to find out what is going on. Why are we getting an induced current? What is that actually telling us? Charges don't just start moving by themselves. Something must be making those charges move. So here we're going to start by looking at this figure that shows a conducting loop in an increasing magnetic field. So we see that we have the magnetic field. The X's are telling us we're seeing the feathers of our arrows. It's going into the screen. And so it's increasing. So if it's increasing into the screen, then we end up with an induced current around our conducting loop. So we can use Lenz's law. According to Lenz's law, that induced current is going to oppose the change in the magnetic flux. Now the magnetic flux, because it's increasing into the screen, we want to have an opposing magnetic field that would be coming out of the screen. And so to have a magnetic field that's coming out of the screen, so you can see it coming out of the screen at you, then my fingers will curl around in the counterclockwise direction. So the induced current will be in the counterclockwise direction. So we know that we have this induced current in the counterclockwise direction, but it doesn't just happen by itself. Something has to act on the charge carriers to make them move. So we infer that there must be an induced electric field. So it's not just an induced current out of nowhere. We're actually having an induced electric field that is tangent to the loop at all points. So our electric field will point tangent to the loop at all points. So let's look at this in another way. Let's now take this, and instead of having a loop, let's generalize it. So here we have, when the magnetic field is increasing in a region of space, we may define a closed loop, any closed loop. We don't have to actually have a loop, a conducting loop in there, but we can define any closed loop, which is perpendicular to the magnetic field, as long as it's a loop that's perpendicular to the magnetic field. If the magnetic field is increasing in a region of space, and we define this closed loop, Faraday's law specifies that the loop integral of the induced electric field around this loop, we take a loop integral around this circle. So we remember that our closed integral around a surface looks like this. So it's going to be, in this case, E dot ds. So it's going to go around that loop. And that we know will be equal to the change in the magnetic flux. Well, the area isn't changing. So what it's equal to is the area times the change in the magnetic field in time. Let's look at a specific example of a solenoid. So here we have a solenoid, and the solenoid, if we remember, is a wire with loops, basically a looped, a coil. And so these, we have a current going in, and in this case, we have an increasing current. And we know that that current, if it's going in this direction, we take our fingers, curl them around in the direction, is going to give us a magnetic field going in the upward direction. So the magnetic field is going upward. So the current through the solenoid creates an upward pointing magnetic field using our right-hand rule. Now in this case, our current is increasing. So if the current is increasing, the magnetic field better be increasing. So as the current is increasing, B is increasing. So if B is increasing, that means that it must induce an electric field. Let's look at how we can induce this electric field and what we know about this electric field. So if we have B increasing, and let's think about it if we had a loop that was inside our solenoid. So we could use Lenz's law to determine if there were a conducting loop in the solenoid, what the induced current would look like. And so we have B increasing. So if B is increasing, we need to have, to oppose that change in the magnetic field. And so in the magnetic flux, to be precise. And so we need a magnetic field going the opposite direction. And so in that case, we would have a current in the clockwise direction. So the induced electric field must therefore be clockwise around the magnetic field lines. So let's now take one of these electric fields, the electric field lines that we have now generated. And let's look at that in more detail. So if we take this electric field circle, the circle of this loop that we've got, this closed loop that's giving us, that we've integrated over. So this is what we just did for our integral of E dot ds. This is what our loop looks like. And now let's look at how we can use Faraday's law here. So to use Faraday's law, we want to integrate around a clockwise circle of radius r. So this is our clockwise circle here. It's got this radius r. So if we integrate around that, we know that Faraday's law tells us that the closed integral of E dot ds is going to be equal to the area times the change in the magnetic field over the change in time. So to do this integral around this circle, well, that's pretty easy because the electric field isn't changing around this circle. That's the whole reason that we picked this circle. It's a point where the electric field is constant around that electric field line. And so now we move our integral sign inside and we do the integral over our whole circle. And so the integral around our circle is just going to be the circumference of that circle. So we see that the integral around of our loop is going to be 2 pi re. Now that's going to be equal to the area times dB dt. And we know the area of our circle too. The area of our circle is equal to pi r squared. So it'll be pi r squared dB dt. So setting these two equal to each other, we see that 2 pi re equals pi r squared dB dt. So I can divide through by 2 pi r. And so I'll divide through by 2 pi r here. And I see that on this side, I get pi. And one of my r's cancel and I end up over 2. So I see that E equals r over 2 dB dt. Thus, the strength of the induced electric field inside the solenoid is going to be E inside is equal to r over 2 dB dt. So we've noticed that changing a magnetic field gives us this circular electric field, which is different from the electric field lines that we looked at before from charges that were moving from a positive point charge to a negative point charge. Now we're getting circular electric field lines around our changing magnetic field lines. So we can think, so Faraday's law and Lenz's law may be combined by noting that the EMF must oppose the change in the magnetic flux. So in this case, we see that a changing magnetic field creates an induced electric field. And so if we combine them, we see that mathematically, the EMF must have the opposite sign of dB dt. So we can write this as, we can rewrite Faraday's law saying that we know that it's the EMF is equal to the closed integral of E dot ds, and that must be equal to negative dpm dt. So we can write it that way, and now we can think about how we actually get these circular electric field lines due to our changing magnetic field. So as we know, changing the magnetic field induces a circular electric field. So we might think that symmetrically, changing the electric field would induce a circular magnetic field. And so if we change the electric field, then we can create an induced magnetic field as well. So now we have a changing electric field. In this case, we're indicating that pointing into the screen. It's our region of increasing electric field, and we end up with an induced magnetic field that is now a circular magnetic field. And this idea of the induced magnetic field was first suggested as a possibility by James Clerk Maxwell in 1855. So Maxwell took the fact that we can have a changing electric field that will create a changing magnetic field and a changing magnetic field that will create a changing electric field. And he put them together and saw that if we have a changing electric field that creates a changing magnetic field, so here's our changing electric field, and it's creating a changing magnetic field right here, so then this changing magnetic field will then in turn recreate the electric field, which then changes in just the right way to again recreate the magnetic field, and so on. This is called an electromagnetic wave, and we will go into more detail about this in the next module. The direction of propagation of the wave is here, and we see that its speed is given as 1 over some constants that we know very well, the square root of epsilon naught times mu naught. Let's look at one of the examples of Faraday's law. We already talked a little bit about generators. That's an example of Faraday's law. Now let's look at transformers. So transformers work by having an alternating current. So that's an alternating current here. I'm sorry, an alternating EMF. So we have an alternating EMF. So it's V1 cosine omega t. So we can see it's an alternating. So we go like this. All right, V1 times cosine omega t. So it's an alternating V1. And it goes through our primary coil. So this is the primary coil over here with N1 turns. Now, this causes an oscillating magnetic flux through the secondary coil. So here's our secondary coil over here with N2 turns, a different number of turns. And hence, on this side, we get an induced EMF, V2. So now we end up with a V2 on this side due to the fact that we had this oscillating magnetic flux through the loops on the other side. So the induced EMF of the secondary coil is what we actually deliver to the load. So we put in our alternating EMF, and this is what's coming out to our load. This is what we're powering it with. And so we see that the V2, what's coming out, the secondary EMF, is going to be related to the primary EMF by the number of turns. So it's going to be N2 over N1 times V1. So that is how we can transform from one EMF, one primary voltage, to a different EMF, a different voltage. We can change the voltage through a transformer by this use of electromagnetic induction. We'll look at some more uses of electromagnetic induction and some more things to do with inductance coming up soon.